Right, so obviously if we just left it like that, so momentum is mass times velocity, that would be nice, but we're not. We're gonna be doing slightly more complicated examples than just P equals mv. So we're going to look at 3 different types of collisions. Normally I would be getting you guys to come up and have a go at the linear track. Unfortunately, we can't share any equipment at the moment, so I'll just be showing you what the type of collisions are. So there are 3 types. There's inelastic, there's elastic, and then there's explosions. Okay, so inelastic collisions, generally what happens is something moves along a track, so let's say this one, and there's one that's stationary, okay, and this moves along, and I'll show you in 2 seconds, hits that, and then they both move off together. That's generally what happens in an inelastic collision. Okay, so let's just show that happening. Hopefully it will work.
Just assuming they're both the same mass.
They don't have to be the same mass, though. Different masses.
Well, I feel like stationary one is like, oh, heavier.
If it's like it,
No,
it still moves slightly. Right, what we can do with that, if we were going to do this experiment ourselves, what we would do is we could use the light gates to measure the speeds before and after. Okay, remember, momentum is mass times velocity, so you can measure the mass of the trolleys or whatever that's moving the carts, and you can measure the speed of this one before. So okay, this is the only one that's moving before. So you measure the speed by going through a light gate. Then you would measure the speed of both of them moving off together after they've collided. Okay, so then you can work out what the momentum beforehand is, and you can work out the momentum afterwards, because you can just use a top hand balance to measure the mass. Okay, and then you can what you would do is you work that out, and you'd find out, if it works, that the momentum before was equal to the momentum afterwards. That means momentum is conserved. That's the principle of conservation of momentum. So in any collision, momentum is always conserved. So P equals mv of that original one is equal to P equals the total mass times by the velocity as it moves off. Okay, so momentum is conserved. However, what you could also do is work out what the kinetic energy is before and the kinetic energy is afterwards. And in an inelastic collision, the kinetic energy does not equal, the initial kinetic energy does not equal the final kinetic energy. So momentum is conserved, but kinetic energy is not. Okay, so basically that's what this experiment would be. So you apparatus setup, linear track is made level, or you use a friction compensated one, which is ours. The masses are measured using top hand balance. Vehicle A is projected through light gate 1. It collides with vehicle B, which is stationary, and both vehicles move as one through light gate 2. The timer calculates the velocities using your normal length of interrupt time divided by time on timer, and the momentum of the vehicles before and after the collision is calculated. Kinetic energy of the vehicles before and after the collision is also calculated. So these are the sort of equations that you would use. So the momentum before is the momentum of trolley A, plus the momentum of trolley B. Okay, so m times v for A, m times u, which is say the initial speed for A, and m times u for B. So u for B, the initial speed for B was 0. Yeah. The momentum afterwards, because they join together, the momentum of A and B together is the total mass of both of them times by that speed that it moves off at. And the kinetic energy before is half times mass times the initial speed squared of A plus half times mass times the initial speed squared of B, which is 0. And then the kinetic energy afterwards is half times the total mass times the speed of both of them moving at the same time. So, conclusions. Now, I typed this up but you have space to write this, I'm afraid, because it's quite a bit of writing and it takes me a while to write it with my pen. So, The important thing here is in the absence of external forces, so underline that or highlight that, in an inelastic collision, momentum is conserved, i.e. momentum before equals momentum after. The kinetic energy is not conserved, so in this interaction, the kinetic energy is smaller after because they move off at a smaller speed. And there's a couple of equations. So mass of A times initial speed of A plus mass of B times initial speed of B equals mass of A times final speed of A plus mass of B times final speed of B. And EK before does not equal EK after. So I'll leave that out for a little bit. Once you've written it, you can just have a read through the next question. By all means, have a go at example 2 if you want to, or if you want to wait for me to go through, that's fine too.
See if the velocity after the crash as well. You have to, are you allowed to say that that's just one of them? Like,
Yeah, you can split them up. Yeah, you can split them into 2, or you can use them, or you can lump them into 1. It works out the same. Is anyone still writing? A couple more minutes. Okay, am I good to move on? Yeah? Right, okay, so example 2. Car travelling at 20 meters per second east, so that was this one travelling at 20 meters per second east, crashed into the back of a stationary vehicle of mass 800 kilograms and locks onto it, so they move off together. An analysis of the accident shows that the speed of the wreckage immediately after the collision is 12 meters per second. So one started off moving, the other one stationary, it hits it and they both move off together. So first of all, calculate the mass of the moving car. So these types of questions, they're all kind of using the similar kind of thing, but you might be finding a different thing. Okay, so you'll see that I would always draw a diagram first of all, just so you can see what's happening. So we've got a diagram there for us. So before, we've got the mass of this unknown travelling car that's travelling at 20 meters per second. And this is stationary. So this is coming along stationary. So this has got a initial speed of 0. But we do know the mass of this in seconds. Then, afterwards, they move off together. So the mass of A plus B is mass of A, which we don't know, plus 800. And we're told that they move off together at 12 meters per second. So we need to use that conservation of linear momentum, i.e. the momentum before equals momentum afterwards. So the mass of A times by the initial speed of A. So MA we don't know, so we just keep that as MA, that's our unknown, times by 20, plus the mass of B, which is 800, times by the initial speed of B, which is 0. Equals the mass of A times by the final speed of A. Now, this is split it up. You can join them together if you want, so you could say mass of A plus mass of B in brackets times by the speed. But actually, it's probably a bit easier if you split them up in this case because you're just finding the mass of one of them. But you can do either way. Either way is absolutely fine. It'll come out with the same answer. So mass of A, again, what we want to find, times by the final speed of A, which is 12, plus mass of B, which is 800, times by the final speed of B, which is also 12. So what have we got? We've got 20 MA plus 0, because 800 times 0, equals 12 MA plus 9,600. Looks a lot nicer now, doesn't it, once you put all the numbers in and work things out. At the start, it looks like there's so many different terms, but I promise you there will only be one unknown term. So now we've got basically something x plus something else x plus a number. So if you were to rearrange that, you would end up taking the 12 MA, so 20 MA take away 12 MA. Equals 9,600. I'm sure you could probably do this in fewer steps, but this is just showing you where I've got it from. So 8 MA equals 9,600. So MA is 9,600 divided by 8, which is 1,200 kilograms. Okay? So it starts off looking complicated, but once you put all those numbers in there, it does simplify out quite a lot. But make sure you do your exam technique, so you put your equation, you write in your numbers, then you start trying to rearrange it. Part B asks us to prove that the collision is inelastic. So remember, in an inelastic collision, kinetic energy before does not equal kinetic energy afterwards. So what we need to do is to find the kinetic energy before, find the kinetic energy afterwards. Do they equal? Write a statement saying they do or do not equal. Okay, so you guys have a go. Make a start on that one. So before the collision and after the collision. Sorry, is anyone still writing this? Am I okay to move on? No, okay. So I'll just write it on the board, but while you do it as well, so we can check that we get the right answer. Have you got this written up here? Yeah. Right, so those are the numbers that you should be getting. So the first one, half times mass of A times by the speed of A plus 0 because the B wasn't moving. So 240,000 joules. And after the collision, it's half times the total mass times by the speed they move off together. Yeah. Oh, yeah, that's fine. Yeah. And then you need that final statement. You need to write a final statement. If they've asked you to prove that something's inelastic or elastic, you have to write a final statement, otherwise they'll take a mark off you. So just something that's saying kinetic energy before does not equal kinetic energy after, so the collision is inelastic. Okay, so I'd like you to have a go at some of these questions before we move on to the next one, although they are all quite similar. So if you just start your question booklet and start going through page 1, so questions 1 to 11, and give me a shout if you're coming across anything difficult. The main difficulty is putting the correct numbers in the correct place.